former captain of the Bronx High School of Science wrestling team, and he's the author of the book that we're honoring tonight, Death by Black Hole and Other Cosmic Quandaries, which is now in paperback by Norton Press. So if you're wondering what a cosmic quandary is, before Neil comes in, I'll pose you three pseudo-cosmic quandaries. What is the highest spot on Earth? And the answer is not Mount Everest. A scoop of which planet, if you scoop a piece of it, will float into your in your bathtub? Why is the statue of Atlas carrying the world on Fifth Avenue across from St. Patrick's Cathedral at Rockefeller Center, that Atlas, why is that statue suddenly more accurate than it used to be? To answer these quandaries, as well as other more profound questions, let's welcome Bronx boy, Dr. Neil deGrasse Tyson. The highest spot on Earth is not Mount Everest, your book says. It's something else. What is it?
First, it's true not because my book says it, but simply because it's true. Okay, let's want to clarify that.
All right.
No, I mean, Earth, to the astrophysicist, we don't really care much about sea level.
No.
If you want to be high, you're measuring your distance from the center of the Earth.
From the very center of the Earth.
Is that different from the center?
I'm trying to
Okay,
give it.
the very center of the Earth. I don't know how many centers you know of. Okay, the very center of the Earth.
The really very, very center
Yes.
of the Earth. Yeah.
So you want to find the farthest point from that center. And it turns out sea level at the equator is farther away from the center of the Earth than sea level near the poles. It has nothing to do with global warming and melting of the ice caps.
Why is that?
Because Earth, we know it spins once a day. Yes, thank you. 3 people know how long a day lasts here.
Good for row number 2. They're off to a great start.
So you spin. You know, when you spin pizza dough, it kind of flattens out.
Yeah.
Gets wider in the middle, and so Earth, throughout its life, even when it formed, it was spinning, and it got a little wider at the equator than it does at the poles. So it's not actually a sphere; it's oblate, and officially it's an oblate spheroid. That's what we call it. But not only that, it's slightly wider below the equator than above the equator.
A little chubbier.
A little chubbier.
Yeah.
Chubby's a good way. It's like pear-shaped.
Yeah.
So it turns out the pear-shapedness is bigger than the height of Mount Everest above sea level.
How much higher is the tall mountain that you identify in this book, which name I forget, and probably you do too, in Peru, or is it Ecuador?
Ecuador.
Ecuador. How much higher, if you were on top of this mountain in Ecuador, how much higher than the Mount Everest would you be?
There's a 20,000-foot mountain in Ecuador, which is right. Ecuador is like near the equator, hence Ecuador.
Oh, you're just not giving up.
And that mountain is actually, the summit of that mountain is 1 1/3 miles higher away from Earth's center than the summit of Mount Everest.
Okay. Question number 2.
But wait, but you got to know, let me just so you understand. We've been fed a lie our entire, I want to call it a lie. We've been fed.
It's a point of view thing, I think.
Earth has been misrepresented to us by geologists. Because the globes that you buy, that you rub your fingers over and you feel the Himalayas and you feel the Rocky Mountains. No, okay? These mountains are puny compared to the size of the Earth. You would not know they were there. If you were truly that size, some big cosmic giant lumbering through space, coming upon the Earth, rubbing your hand on it, the depth of your, what do you call these?
Your finger.
The fingerprint mark. The depth of that would be greater than the entire range of distance from the Marianas Trench in the bottom of the Pacific to the top of Mount Everest. Therefore, you would close your eyes, rub your finger, you would not know whether you are on ocean, valley, mountain, or hill.
Well, you might be wet or dry. You might be,
Well, by how much wet?
A little.
How? No.
Yes.
You wouldn't even notice it. You're not going to say, oh, I got to dry my hand. The depth of the ocean doesn't measure up to the depth of your fingerprint. That's my point.
Oh.
So we've been fed this misrepresentation of our own planet on the belief that, in fact, we have real surface features. But cosmically speaking, we're practically a perfect sphere.
Riddle number...
I sound disappointed people there. I'm just letting you know.
Well, I don't know.
This is like the planet you live on, just so you know. Oh, by the way, how pear-shaped are it's like, a dozen, 20 miles. It's in the teens. So it's not that much. But Mount Everest is only 6 miles above sea level. And Marianas Trench is 5 miles down. So the distance from the bottom of the lowest point on Earth's crust to the highest point is less than the length of Manhattan. Less. You can drive that. The height of Mount Everest is 6 miles. That's 10 kilometers. People just run that. The problem is that's straight up. It's up, of course, but it's not as far as you think. Just put that in perspective.
A scoop of which...
Wait, is that the biggest quandary you could get
Well,
out of
no,
the book?
it's one
We
of
got
the
people getting
quandaries.
ripped apart. You're asking me about... Okay,
well, I'll
go.
get to the rip apart. I thought I'd start low. We kind of scale up. A scoop of which planet, if you scooped up a piece of it, would float in your bathtub?
This is a quiz. In case you didn't know, we happen to live on a dense planet, Earth. Okay? I was referring to the material, not the brain power of who...
Except for row 2.
We live on Earth. It's dense, and so too is Venus and Mars and Mercury. We're rocky planets. Then you go beyond the asteroid belt, you get the big bulbous gas giants. They're all very low density, beach ball-like. Jupiter, Saturn, Uranus, and Neptune. Among them, Saturn is by far the least dense. In fact, it is less dense than water. And anytime you have those conditions going for you, you will float in a bathtub. In fact, when I was a kid, I knew this, like when I was 10 years old, and I wanted, instead of a rubber ducky, I wanted a rubber Saturn that I could play with. And people just thought I was weird.
Why is the statue of Atlas carrying the world on Fifth Avenue suddenly up to date?
Ooh, that's a good one. Atlas, Atlas. Plus, I think he's carrying the universe, not just the world.
Okay.
And in the old days, it was the known universe. I mean, he was carrying not just Earth, I think. It was the whole world. World, that's capital right. W, right? That statue was designed in the 1920s. It actually wasn't put together until the 30s, but it was designed in the 1920s. And the way the sculptor represented the universe was on the yoke of Atlas's back. He put the symbols of the planets. And so he's got Mercury, there's a symbol for Mercury, Venus, Earth, a little symbol for the moon sitting next to it, it's kind of cute. Mars, Jupiter, Saturn, Uranus, and Neptune. Okay? Atlas is Pluto-less. He's Pluto-free because he was designed before 1930 when Pluto was discovered. And then Pluto got discovered, but he's already kind of put together. And so he was missing a planet for 65 years until we came along and asserted that he's right on cue again. I hear some Pluto lovers out there.
Yeah. Thought we
Look, I was just in Disney World, and I told Pluto, I got VIP to come in the back, and Pluto's there, and I whispered in his ear like that I had something to do with this, and he looked real sad afterward. We should have brought the picture.
Was there a relationship, by the way? Did Pluto get the name in part? Because I think probably the cartoon character came to be roughly around the same time.
No, exactly the same time. Yeah. Pluto the dog, which in case, this is the Upper East Side, I don't know how much Disney you know, but Pluto the dog is...
Row 2, actually, they're all weird.
The dog, it's Mickey's dog. Mickey Mouse's dog is named Pluto. And I've always wondered, of course, what does that mean? Why is Pluto Mickey's dog and Mickey is not Pluto's mouse? I've always been troubled by that. But then I had to get to the bottom of that, and then I learned.
There's an answer to this?
I called top people at Disney,
yeah.
Okay?
Yeah.
Here's how you can become the pet of another animal. The rule is, if you don't wear clothes, you can be a pet. And Pluto runs around butt naked, whereas Mickey wears the bow tie. So Mickey talks, Pluto barks. That's how that works. In case you didn't
There
know.
is also this thing. Mickey never seems to. He has always wearing gloves. I mean, apparently, if Nicky has nails, we're never allowed to see them. Just thought I'd throw that in.
That would be
yeah.
true, but wouldn't they be claws though?
Or
He's
claws.
a rodent.
But he's got white gloves. He's like dressed for high tea.
right with
at all
3 fingers on it.
Yeah,
too.
yeah. All right. Well, now that we've
Cleared
cleared
that
the big
up.
ones.
Well, where were we going with that?
Well, I don't know. I'm going to try to take it some direction or other. The book's introduction says that there was once a time when really important physicists, felt that all the big problems of physics had been kind of figured out. You then comment in the introduction, but our species is dumber than we normally admit to ourselves. And you list a bunch of what you consider really interesting unanswered questions. So let me just take you through some of these, because they're your questions, or they're everybody's questions. The first one is, how did the universe begin? Like, what started it? You have nothing, and then you have something. Like King Lear said, nothing comes from nothing. So how do you, let's start with, how do you get from nothing to something?
We have no idea. So next question.
Yeah.
Okay.
Oh,
We got top people working on that one. Okay.
and they all have pets, butt-naked pets.
Actually, it's not that we have no idea. We have some rather interesting ideas, and they're all traceable to the concept of the multiverse, where we, in our friendly universe with known laws of physics, are just one bubble of many bubbles that would come in and out of existence in this sort of meta system of multiverses. And if that's the case, then we can definitely point to a beginning of our universe because there's some other structure that's there pumping them out and pulling them back. But that just simply shifts the question to how did the multiverse get here?
Yeah,
And we
that
have
doesn't
no
seem
clue.
like a very, that's sort of a turtles all the way down kind
Yeah,
of.
in principle it could be, unless the multiverse was always there. And I know that's philosophically unpleasant, but if you're exploring open-minded to what is possible in the universe, quantum mechanics looked really weird to us in the 1900s, in the early 1900s. Just because it looks weird doesn't mean it can't be true.
So does that mean that what we think of as nothing is actually more than nothing? So
Yeah, there are levels of nothing. For example, if you go out into space, where there's no air, you'd call that nothing. But now sort of leave the universe where there's not even space. That would not even be nothing. If space is nothing, and then you don't have space, what else are you going to say? It's not even nothing. Or rather, we have yet to come up with a word for it because we don't understand enough about it to name it.
what about the idea somehow that something pops into existence? Okay, so we'll call it
Wait, by the
matter.
way, he's going to ask me all these questions about which we have no answer. Yes, that's part of the book, but there's a lot of other kind of known stuff in the book too.
Yeah,
right?
yeah.
You don't have to just be depressed that we don't know what's going on. Just want to clarify that.
This is a subset of the question. We'll skip over the part we don't know, and we now look at the stuff that pops up. So it's something called matter, but you do describe that for everything that we observe, every proton, every neutron, every electron, there seems to be a equal and opposite thing carrying an opposite charge. So for the sake of vanity, I guess we call it antimatter. But the question is, and when they meet, they essentially annihilate each other.
They're not even essentially. It's just annihilate.
So how
No
come,
modifier necessary. Yeah.
but still we're here. So if every electron in you, every neutron in you, and every proton in you has an equal and opposite and antagonistic opposite, why aren't you popped out of existence before you even start?
Because in fact, not all matter particles have opposites in this universe.
And isn't that a mystery?
Yes, it is. One of the most interesting mysteries of the early universe. And if I may give some background on that.
Sure.
14 billion years ago, or if you want to be 3 decimals precise, 13.7 billion years ago, the universe was much smaller, much denser, much hotter. So hot that matter and energy formed this soup of interplay. Right now, you take it for granted that we sit here and you're not going to pop into a ball of energy and dissipate into space. We kind of expect that that is not going to happen quite that way to you. And so why? Because we don't live in an environment for which that's an everyday occurrence. But there are environments in the universe where that happens all the time. Like, for example, the center of a star, at the origins of the universe. In fact, if we were immersed in those environments and did not otherwise vaporize, it would be a very natural thing to watch particles pop into existence out of nothing, but it's actually energy, and watch particles come back together and make energy again. That's a very natural thing, exotic to us, requiring an Einstein to have figured out. But under some conditions, it's just every day. So you go back in time, and you say, here is this ball of energy. And as the universe cools, the energy spontaneously becomes matter. Now, if you're hot enough, that is a two-way street. Matter becomes energy, energy becomes matter. But as the universe expands and cools, you reach a point where the pool of energy is no longer high enough to make particles. Okay. Well, if that's the case, all matter and antimatter would come back together, annihilate, make a beam of light, and all we have in the entire universe are beams of light. Okay. But that's not the universe we live in. The universe we live in has an imbalance of matter and antimatter. In fact, for every 100 million matter-antimatter particle pairs, there was one surplus matter particle without a counterpart. And it's a big, mysterious asymmetry. We don't know what caused that asymmetry. We have some ideas, but we don't know for sure. But there's that asymmetry, and all stars, galaxies, planets, gas clouds, light, everything you've ever thought of as a thing is made out of that 1 in 100 million particles that did not annihilate. And everything else is just light. And that light we see, in part, as the cosmic microwave background in the universe.
You know, it's like a whew. You know, we got lucky. Or
there's 100 million other universes where different laws of physics unfold, and we could only be having this conversation in the universe for which that's true, which then doesn't make us lucky. It just makes it sort of the reality of the moment. I'll give you an example.
Okay.
I'll give you an example. Try this experiment. And I encourage you, yes, do this at home. Yeah? Okay. Take a coin. Actually, this would be really hard to do at home, but it's not dangerous. Get 1,000 people, line them up. Then get 1,000 coins, identical coins. Hand them the coins. Have them flip. Whoever gets tails, have them sit down. That'd be about half, if it's a fair coin. So 500 people sit. The rest do it. Flip. The 250 people sit down. The rest flip. 120 sit down. The rest flip. 60 sit down. Boom. 30 sit down. 15 sit down. 8 sit down. 4 sit down. 2 sit down. We got 2 people left. They flip the coin. One gets the tails, one gets the head. One person is left after all of that. Okay? And they win a prize or something. And he asked that person, what do they have to do to win that contest? They have to flip a coin, heads, 10 consecutive times. And almost every time you do that experiment, somebody's going to flip a coin 10 consecutive times. Now, our human brains are not equipped, not trained to understand the statistics of that. So you know that's who all the cameras go to. And they say, well, how do you feel about this? And you know what the person will say? You know, I knew I was going to win about halfway through. I had those heads vibes. You know, I woke up this morning and I knew I'd be lucky. Now, of course, they're not interviewing the other people who felt the same way but lost. Okay? They're not interested in the interview because they didn't win the prize. And so the idea that you were chosen among others, it's hubris to suggest that the whole thing was special just for you. And so I'm here to appeal to your sensibility that whatever is true in the universe, the history of our discovery tells us that we are just simply not special. And if you ever come to an idea that says we're special because we're lucky, you pause for a moment and look at the history of those thoughts and how wrong they have been. And then step lightly as you go forward.
Okay. Let's, it's very
So if any journalists out there, the next time a person wins the lottery, Go interview the people who didn't win and find out what lucky numbers they played, okay?
What happened just before the Big Bang?
You asked that. I said we have no clue.
And let me follow that up. What is wrong with the word before? Is this a question of when did time start, or just to deal with that?
No, there's nothing wrong before. We just don't have any data. We just don't have any data. I don't mind going into negative time. I have no problem with that. I don't mind resetting where the 0 point is. Time is just, where you put the 0 is arbitrary, as it continues to be this day with calendars. We use a Christian calendar that's related to Jesus. Muslims got one related to Muhammad, and the Chinese have one, and I forgot who they dated that from. The Jews have, everybody's got a calendar with their starting point. And so the starting point is just where you want to put it. And so right now, a pretty good starting point is the Big Bang. We don't know how to put it earlier than that. But if the day comes where a whole new kind of understanding of the universe reveals to us before that, I don't have any problems pushing the 0 point back or just counting into negative years. I don't have any problems with that.
You have no problems with it, but is it something that we could one day look forward to finding the answer to, or do you think that there is some kind of barrier between the word before and the answer to the question?
I am undaunted by the limitations of words we use. Just because we date the beginning of time at the Big Bang does not prevent me from thinking about before, even in the absence of data. I'm open to what could possibly be going on before the Big Bang, number one. Number two, right now we have no clue how to look there. We just don't. Do I think there's a forever barrier? That simply wouldn't be wise, given the history of science, about which I do a fair amount of study. And I take my cues from great thinkers of the past, some of whom believed they had hit a boundary, believed the end was right there in front of them. And then sure enough, a cleverer person than they comes along and says, well, you idiot, just sit down and get out of my way. There's a problem I'm solving. And they don't call them idiots, but it's a lesson in the belief that you happen to be alive at a time where we've reached the end of knowledge. That itself is hubris. That itself has the implicit assumption that you are smart enough to know that we've reached the end of knowledge. Admit the possibility that someone could be born after you who's cleverer than you, cleverer than me, who will solve all the problems that we are now scratching our heads over.
All right, I'll give you another one. Let's go to as far as you can see. So you look out that way, 13.7 billion light years, or that way, which way you want to look. And the question a lot of people wonder is, so what is on the other side of that horizon, cosmic horizon?
That's an excellent question. We don't know for sure, but we have very good reason to believe we do know it's there. And this is a little tricky to explain. But if you're with me out there, because like I can almost barely, I see like the front 2 rows and the rest is just, so I don't know if you're asleep by now or not. Is the back row? There's the back row, okay. All right. I would count that as evidence that the horizon is in view. All right, you got to sort of bear with me for like 90 seconds. I think I can do it in 90 seconds.
Okay.
Because light does not travel at an infinitely fast speed. Travels 186,000 miles per second. That's fast, but it's not infinite. It's so not infinite that you would be frustrated having a phone conversation with someone on the moon because the delay is 3 seconds. You would speak, and by the time they heard you reply to them, 3 seconds would have passed. It would not make a good phone conversation. That's how long it takes the light just to get to the moon. It takes 8 minutes, 20 seconds to get to the sun. It takes 100,000 years to cross the galaxy. It takes 1 billion years to get to the distant galaxies. 13.7 billion years to cross the known universe. It takes time. All right. Put a pin in that fact. Another fact. The universe had a birthday 13.7 billion years ago. So imagine a universe that is infinitely large. Now, put yourself in the middle, and I tell you this universe was born 13.7 billion years ago. So let's go out to the circle, to the sphere around us, go to the spot that's 13.7 billion light years away. In other words, go to the spot where light from objects has taken 13.7 billion years to reach you. You're going to be watching that object being born because its birth light is just now reaching you. Come in a little bit. You're going to see those in their toddler years. Come in a little, they're in the adolescence. Come in a little closer. Come to the present day, and you see everyone in their modern day maturity. So there's a limit to how far you can see in an infinite universe if the universe had a birth date and the speed of light is finite. Wait a billion years. Now the horizon is 14.7 billion light years away. Now you're seeing those galaxies get born. So the interesting thing about the universe in which we live, as long as there's galaxies that get overtaken by this expanding horizon, you will always bear witness to the birth of the universe because somebody is always being born. The interesting part is if the signature of the Big Bang goes away, that would tell you that your horizon washed over a region of the universe where there are no more galaxies to show you their birthday clothes. That would tell you that you in fact reached the edge of the universe. Right now, we can only tell you about the edge of our horizon, but that is an ever-expanding horizon that's still delivering up the signature of the Big Bang.
Is that a function of how well we can see and the tools we have to view, or is it a function of the fact that the space of our universe is expanding?
It's just the physics of the universe. While it's different physics, it's the same notion that if you're a ship at sea, your horizon is the same distance in every direction, and you can't see beyond the horizon. But you know the ocean continues. So in fact, if you moved a little closer in that direction, more of the ocean comes into view. So that's why we feel really confident that however big the universe is, it's bigger than our current horizon because we're watching the universe get born.
Are we also confident that we're
5 billion years ago, we could have watched the universe still being born. Who would have been being born 5 billion years ago? The galaxy is 5 billion light years away.
What happens when the galaxies over there are really, really far away from the galaxies over there? So if you
everybody's got their own horizon. Yeah. So we are on the edge of a galaxy's horizon 13.7 billion light years in that direction. Mm-hmm. They see us, our light from 13.7 billion years ago is only just now reaching them. So they see us going through the birth of the Big Bang. We are their Big Bang signature right now. So everybody's got their, just like every ship at sea has its own horizon around it.
I do get the sense, though, that physicists have now developed
I'm screaming at you. I'm sorry. I'm screaming at the microphone.
No, it's okay.
What happened here?
That physicists... There's a kind of neighborly thing beginning to develop, and I want to ask you about it. If I were on a galaxy 37, 13, whatever it was.
You didn't say a galaxy far, far away.
Galaxy far, far away in that direction. I would have no information about a galaxy equally far in the from Earth in the other direction because it would be too great a distance from there to here.
Yeah, another way to say what I just said is go to the 13.7 billion year galaxy. We come to us. We are being born to them. The galaxy 1 billion light years there, its birth light has not yet reached that galaxy. So it doesn't know anything about the stuff to my right.
Yeah.
But wait another billion years, enough time has passed so that that galaxy's information has reached.
So I used to think that the word universe meant the whole thing and that there was only one.
We have to specify, there's the observable universe, and then there's the universe that the observable universe is, the light cone is expanding into.
Right.
Yeah, so often when we say, how big is the universe, we're giving you the observable universe. How many stars in the universe? 10 to the 21 stars, a sextillion stars. That's in the observable universe.
There is
when in doubt, assume observable universe.
All right. But my use of the word universe used to mean everything that there is, which seems to be different from everything that one could know, see, touch, feel, learn about. So that the is may be bigger than the know. Certainly the folks all the way over there can't know about the folks all the way over there.
That's correct.
So why do physicists now begin to talk about universes? Are they saying that the folks who cannot know about the folks over there are in a categorically different place because there is no information from there going to there? Are they
I'm
in
talking about a whole other zone where it is likely that the laws of physics themselves are different, however slightly, from the laws of physics in this universe. The multiverse prescribes the fact that you would have variations in the laws of physics among the universes. That's the example with the coin. We are speaking from a universe where the laws of physics allow life.
Let me ask you this more
So are we
precisely.
special, or are we just the person who flipped heads 10 times?
When you use the word universe in the plural, when you say universes, are you thinking of distinctly
Yes.
isolated
Yes.
neighborhoods in a common place?
No. I'm
So-
thinking of distinct. We all share the same laws of physics, even the ones outside your horizon.
So
we are a family.
We are family. So the gravity exists for all of us.
Yes.
Entropy exists for all of
Yes.
us. Strong forces, weak forces, electromagnetism for all of us.
Yes.
There's an elementary table that exists for all of us in this
Table of elements. Yeah.
table of elements. But so then, and then around us, beyond us, there is a place where you might go and have all the rules different.
Yes.
Even the rules of physics. Even the
No,
rules.
that is what would be different. Everything issues forth from the laws of physics. Now, what that means
Why
is...
do you need
Well,
this?
what that means is you don't want to be the first explorer in this other universe, okay? because you know, you're kind of held together by these laws of physics.
Yes.
And if the charge on the electron were just slightly different, you could explode or implode, or you want to send the probe, the test probe first. Then you come later, just so you know, in case it ever comes up.
Why would any intelligent person need to conjure up a place, a big, expansive place, where the rules, the basic rules, are different? Why does anyone talk about that? In my ordinary life, going, having breakfast, going to work, coming back home, it just never comes up. No one ever asks me about other universes and other rules of engagement. I'm kind of content to know that, as barely I can make them out, the rules that Einstein and his crowd sort of figure, well, they fit, and I'm okay with that. Why is there this need for a non-fitting set of places?
I don't think of it as a need. I think of it as the urge to understand your place in the universe. And that urge crosses cultures and has existed throughout time. It's just that the scale is different. Why is this question different from sitting there in the cave, chewing on uncooked meat, looking across the valley and saying, I wonder what's on the other side of that valley? I want to try to find out. But your counterpart back then would say, why do you need to know that? You got your, pterodactyl leg or whatever you're chewing on. It wouldn't have been pterodactyl. You got your saber-toothed tiger leg, and because you just lost your friend, in the tar pit. And you're saying, I got my food, I got my crib. What do I need to look on the other side of the valley? But then you find out on the other side of the valley there's water and fruit and fire and stuff that you can use. You don't know how to use it yet. You figure out how to use it, okay? So the frontier of human exploration has always delivered dividends on who and what we are in the lives we lead. And some deliver more dividends than others. Now, you might think, another universe with different laws of physics, how could that possibly relate? And right now, I don't know how that could relate. I'm not going to pretend to have a whole list of how I'm going to invoke it tomorrow. But I look at the history of science, the history of discovery, and I will not deny our species the privilege, if not the obligation, to look beyond whatever is your perceived horizon of the moment. And by the way, we live in a wealthy nation, and wealthy nations, it's kind of, that duty falls on them because they don't have to worry about where the next meal is coming from. They have enough money to sort of pay everything out and save a little bit for that exploration. I'm proud and privileged to be part of a species that has people that want to do that. I joke with people who climb mountains and put their lives at risk, but that soul of exploration is what creates the urge to want to know what these other universes are like.
Well, let me go from a question of wealth, which is asking too many questions, to the utter poverty of one of the chapters of your book. In one chapter, you say, you know what? We don't know when we look up in the night sky and we see stuff, and we look down at our shoes and at wood and at glass, and we see stuff, and we look at the stars and we see that stuff and the galaxies and that stuff turns out to be a little of what's in the universe, but not most, not much.
It's 4% of the total universe. Everything you know and love is 4% of the total universe.
When did
all matter and all energy that you know and love, all the photons of light, all the particles of matter, when you add it all up, it's 4% of the total energy budget of the universe.
That's sad.
Are you sad that it's that little, or are you sad that we have no clue what the other 96% is? Which of those two facts makes you sad?
Well, the book consistently makes the case for how dumb, uninformed, and in the dark we are, and this pretty well clinches the argument. If that much of everything is missing and comes with no explanation, and yet is plainly, apparently doing things, I mean, the reason that galaxies seems to hold their shape is because there's this invisible stuff that makes them do so.
Dark matter, for lack of a better word. We don't know what it is. It's a source of gravity whose origin we have no clue. Dark matter. So we call it dark matter. We don't even know if it's matter. But it's a source of gravity that exhibits itself in the cosmos. There's 6 times as much of that as there is ordinary matter. So that was our first encounter with total stupid ignorance. Then, 10 years ago, or 1998, it was published in 1998, we discovered 70% of the rest of the universe is this mysterious pressure operating opposite that of gravity that's making the expansion of the universe accelerate. We don't know what that is either. We call it dark energy. So you have dark matter and dark energy combined make up 97% of what's going on in the universe. We have no clue what either of those is composed of.
So on another term...
No, wait. Now, we're not as stupid as that might sound. We're not inventing sort of angels on the head of a pin. This is not the case of the ether in the 19th century, where we knew waves had to go through a medium. Sound moves through air and through solid objects. Light is a wave. Space must have some medium out there. Let's call it the ether. The ether was an invention. There was no evidence for the ether. It was an assumption. And then it went away when we found out light doesn't need a medium in which to vibrate. It can travel through empty space just fine. We call that nothing. Okay. Now, turns out, dark matter and dark energy, we measure it. It's there. We're not inventing a concept. These are just words. They're placeholder words. There is this entity that has gravity, and we don't know what's causing it. But we know where it is. We know how much gravity it exhibits. The acceleration of the universe, we can measure its effect on the expanding fabric of the cosmos. We don't know what's doing it. So we're better off than the ether people.
All right, I'm going to switch gears because the first half of the book does definitely impress you with how little we know, even though it starts with all these guys in the 1880s saying, we know everything, it's all over, the end of science, we're fine. And then you read and you read and you think, we know less. And then we get to the subject of life, and then you turn sort of buoyant in this book. I'm not sure why, but let's go do it. The question here is, why is there life?
Buoyant. Life is a
and
buoyant.
then are we alone? So let's just do this in order. Why do you think there are living things? There is absolutely no necessity for dust to aggregate and become vital, let alone think. Do we know why we have life? I guess not. But
why? allow me to address that.
Yes.
If you look at the chemical ingredients of life itself, you remember from biology class, we're mostly water. And good old water is H2O, 2 hydrogens, 1 oxygen. And if you could look at the sort of the element budget of life, hydrogen is number 1, as expressed in the water molecule. The number 2 in the human body is oxygen, turns out. Number 3 in the human body is carbon. 4 is nitrogen. 5, you find on all lists, is other. Okay, now if you go to the universe, that's the O on the periodic table. You didn't know that? That's not for oxygen, it's for other. So you go into the universe, number 1 ingredient in the universe is hydrogen. That was true in life. Number 2 ingredient in the universe is helium. We don't have that one.
It doesn't like
but
anybody.
now, how come? Well, because helium is chemically inert. You can't do anything with it even if you wanted. You can inhale it, okay? And sound like Mickey Mouse, yes. Next in the universe is oxygen. Next, carbon. Next, other. Thank you, in the 3rd row there. So, actually that was the 2nd row. They must be related to the 2nd row here. We are 1-for-1 matchup with the most abundant ingredients in the universe. Of these, carbon is the most chemically fertile element in the entire periodic table. You can make more kinds of molecules with carbon than all other molecules combined. So, if you were going to experiment through the forces of nature with complex chemistry, and you had to pick an element to base it on, carbon is your man. Or your woman, however that goes. Okay, so what I'm saying is, given what carbon is capable of doing, perhaps we shouldn't be so surprised that there's life, because we are carbon-based life. We're just another one of the things carbon has rolled up its sleeve. Maybe life is inevitable, given the abundance of carbon and oxygen and nitrogen and hydrogen in the universe. Try to invert that view. Otherwise, you're left thinking, hey, we're special. You know I would give you right to say you're special? If life on Earth were made of an isotope of bismuth. That stuff is nowhere in the cosmos, and then we're made of it, we're special. Okay? But if we're the most common ingredients of the matter that we know and love, you don't have an argument.
Well,
Let
me just make sure I understand what you're saying. I don't know that everybody in this room or everyone in the world would think that life is merely an aggregate of the right chemicals in the right order, all holding hands in the right way. You get your carbon, you get your oxygen, you get your nitrogen, you get your hydrogen, and you put it all in the right way, and bing, up comes a little cell, and then you get a bigger thing, and then you get a fish, and then you get a you. It may be. Is that your view? That the world is pregnant with life because all life is a chemical machine arranged in some lucky way. You don't even like the word lucky. In some...
Yeah, was the guy lucky over here?
Yeah, never mind.
Okay. I thought we got through that.
Yeah, okay, we did. Is that right? That's your view?
I'd rather say it a different way.
Okay.
I'd rather say that given the chemical fertility of carbon and the abundance of all the ingredients in the universe that is fundamental to life as we know it, I'm not given any reason to doubt that the formation of life from out of chemical soups brewing either in our solar system or across the galaxy or the cosmos itself, I'm not given reason to believe that that should be a rare phenomenon.
Your friends of life in the book are, you like liquid, because liquid just seems to slush
Life as we know it.
Life as we know it, sorry. Carbon, I guess planets with hard surfaces would be good, something like a rock occasionally. I mean, maybe you could have...
I don't know. We just recently learned that most of the biomass of life on Earth is probably living beneath Earth's surface, in the nooks and cracks and crannies of Earth's crust, where the number of ways and places to live vastly exceeds the number of niches that exist on Earth's surface.
At least they're rocks. I mean,
what I'm saying is, to say you need a surface, I don't know that you need a surface.
I just maybe, if you're going to be in Saturn, you're just kind of dealing with a cloud. Maybe you could grow in a cloud, but at least if you have a rock or something.
Wait. Do fish care that there's a surface? No, because they're swimming through a liquid. They're swimming through a fluid. They don't care. Fish don't go down to the ground and hang out unless you're a catfish. Okay? They're swimming. So why can't there be swimming life in the atmosphere, in the gaseous atmospheres of the Jovian planets? There's nothing in principle that should prevent that any more than life swimming in the ocean is prevented just because you think we need a surface to live on.
All right, let me just ask you about your, because here you seem to be on the joyous side. If I ask
Buoyant was your earlier adjective.
Yes. Well, because that was too fishy for me now. Do you think that life is a fluke, obviously you think it's likely. Let me ask it this way. Do you think because of what we have all learned, say, in the last 10 or 15 years, there's Titan and some of the other, maybe Europa.
The moons
Mars,
are the outer planets.
Maybe moons. Is your bet that there is life all over now a more promising bet to you, do you think, or about the same?
Oh, the likelihood, the prevalence of life in the galaxy, if you can quantify that somehow. I don't know how to quantify it just yet, but imagine that's a quantifiable entity. The prevalence of life that we presume to be out there, the stock in the prevalence of life has gone up in the past 10 or 15 years.
Why?
Because, for me, the best argument for upping that stock value is the following. I don't know the age of everyone in the audience, but I would bet that when you took biology class and you learned the age of the Earth 4.5 billion years ago, that's if you took biology in a school where that's taught. Okay, 4.5 billion years. And then you look at the earliest evidence for life, fossil evidence of life on Earth. Then you get about 3.5 billion years. Subtract those two numbers, get the difference between those two numbers, and that's the time clock from beginning to the first evidence for life. Okay?
So the first.
So that was about 1 billion years out of the 4.5 billion years that Earth has been here. So that's pretty quick. It happened in like the first 20% of the life of the planet.
And the first 20% was pretty rough. There was a
Wait, no, hold on. Now, since the time we all took biology, we have found fossil evidence of life farther back in time than 3.5 billion years. Yeah. It now goes back to 3.8. There's some evidence it might even reach 3.9. So we have shrunken the time available for life to have formed on this Earth. That makes it more likely. If the faster life kicks in from a pool of just random chemicals, not random, they're the chemicals of the universe, the faster that happens, the more confidence I have that life is something that would happen just given the right soup and soup starter, okay? Now, we then learned, when computers got good, better than they once were when we were in school as kids, that the early universe, the early solar system didn't just simply make the sun and the planets. There was debris all scattered in interplanetary space. And that debris slowly got vacuumed up by the gravity of the respective planets. That would not have been a pleasant occasion on the surface of those planets. Because to vacuum it up simply means you're getting slammed by the kind of asteroid that took out the dinosaurs, except you're getting that monthly. And you can calculate what the temperature of Earth's surface would have been. And it would have been higher than what would allow complex molecules to form. Because at high temperatures, you break apart molecules. So, what our computer models show is that this period of bombardment, period of heavy bombardment is the official phrasing, lasted 600 million years. So it's not fair to start the life clock at 4.5 billion years ago, because life had no chance of forming when the surface of the Earth is molten. wait for things to cool down. When there's a chance that carbon can run its magic, then you start the clock. Now you're going from 4 billion years ago into 3.8 billion years. And you have pinched the time it takes to start life down to 200 million years, down from a billion years that was imagined just a generation ago. And that is further evidence that practically the earliest life could have formed, it did. So just because we find it hard to do in the laboratory doesn't mean nature found it hard to do as well. And the idea that it's hard for nature to do because we can't figure out how to do it yet, that itself is an inexcusable expression of human ego.
All right, let me finish the thought. Row 2 seems to like life. Okay. What about, just to finish it off, intelligence?
We're not finished yet, are we? We finished?
No.
Oh.
I know. I'm just coming to the
time
last
is it?
page here. Last page. Intelligence. Intelligence. Now, it's one thing to say, okay, meteors coming in, much too hot to do anything.
What that was? I didn't know what that was.
That was the. That was the.
You said intelligence. Let's say, where's he going with that? I don't know what that is.
That was the soundscape of early Earth.
Okay.
So you have this meteor bombardment, which you just got in stereo, and then, as soon as possible, life starts. Now comes the amazing thing. Somehow, these atoms come, and then the molecules come, and then the molecules gather, and then they somehow get a little window around them or something, and they start conjoining, and then they make fish and stuff. And then one day, one of these life forms says, hello, or something to that effect. So the hello, that's an interesting moment. Do you think that there has been one hello in the history of all things? This isn't a gut question.
On Earth or in the universe?
In the universe. Or, in other words, that this is an unbelievably unusual accident, that atoms would start thinking about themselves? Or do you think it could happen, has happened, may happen over and over again?
It is a pretty cool thing that the universe has conditions that allows it to create matter that then contemplates the conditions out of which that matter formed.
Yeah. I would sometimes think that a physicist are the atom's way of admiring themselves.
Yes. So, now, as you correctly surmised, many places in the book, I try to keep people honest about our self-assessment on Earth, among all creatures on Earth, and in the universe. There's a very, very noble tradition of this. It's known as the Copernican principle, where just when you thought you were special, you're probably not, so get over it, okay? That's the paraphrased version of the Copernican principle. So, you asked me about intelligence, presupposing that we, as human beings, are intelligent. Well, of course, we define the word that way. So we assert that we are intelligent. But let me offer you a perspective that might force you to take pause on that assumption.
Okay.
What I'm about to say is, in fact, not in the book, but will appear in an essay I just finished for Natural History magazine, which is the source of essentially all the material for this book, where I've been writing a column for the past 10 years. But the April essay, for me, will be my 100th essay for Natural History magazine. And the editor granted me free rein to just say whatever the hell I want. And so in there, the title of that essay is called The Cosmic Perspective. And it is an assessment of our place in the cosmos. And let me offer you one of those perspectives, okay? Let us for the moment assert that we are the only intelligent species that Earth has ever seen. That's not much of a stretch. Yes, whales are probably smart, but they don't have opposable thumbs, so they can't build stuff, all right? So we can do things with our intelligence that other possibly intelligent creatures cannot. So we can construct a list of what it takes to be intelligent for which we are the only satisfiers of those conditions. So let's assume we've just done that.
Okay.
All right. Now, here's a thought that keeps me awake at night. Let us look at the closest genetic relative to human beings. That would be the chimpanzee.
The orangutan.
Is that right? The orangutan?
I don't want to quibble.
Is it the orangutan?
The second row will answer. I don't know.
Second? No, I'm almost certain it's the
I think
chimpanzee.
it's the orangutan, but maybe it's... Anyway, let's make it a chimpanzee.
Well, what's kind of interesting there is that we and the other great apes, the chimpanzee, the orangutan, and the gorilla, are closer to each other genetically than any one of us is to the monkeys, those with tails. All the great apes have no tail. Last you checked, you will confirm this. But be careful as you ask the gorilla to show his rear end to you. But you can just believe it. The gorilla has no tail. So it won't, what I'm about to say, it won't matter which of these you choose. I'm choosing the chimpanzee because it's traditionally considered our closest relative. And if you look at the genetic code, it's nearly all identical, except for maybe 1.5%. And that's even been debated. It might be 5%. But that actual number doesn't matter from what I'm about to say.
Okay.
All that we care about is that that's our closest genetic relative. Okay? Can you imagine teaching trigonometry to a chimpanzee?
No.
No. Okay. Can you imagine teaching the multiplication table to a chimpanzee?
I can imagine trying, but I don't
Trying.
expect... Yeah.
They're not going to get it. Yeah. Long division.
No.
Okay. Now,
I had...
you what?
Never mind.
Okay. So, yet that's our closest relative. If that's our closest relative, and it can't learn the times table, maybe the difference in our intelligence is not as big as we think. Let's do the following experiment. Imagine a creature with the same increment in intelligence above us that we are compared with the chimpanzee. That increment in intelligence would only be represented by a small difference in DNA. But imagine that intelligence. That would be extraordinary. To them, their toddlers would be intuiting calculus while our toddlers are learning their ABCs watching Sesame Street. Calculus would be self-evident to their toddlers. By the time they're in their teens, they'd be looking at Isaac Newton and Galileo and Copernicus and Einstein as drooling, doddering fools, the way we look at chimpanzees that figured out how to put a stick in the termite mound to pull out the termites. So maybe this measure of our intelligence is actually not that great, but we've made it great in our own measure of ourselves just to distinguish us from the rest of the animal kingdom. But it's not hard to imagine the same small genetic difference above us, and we would just be their slaves, okay? We would have no power over them whatsoever, because their most trivial of thoughts would be the greatest thoughts our greatest thinkers were ever capable of. And
Wait, don't get so impressed. Let him bring these people to life first.
all I'm saying is, why aren't we thinking about that level of intelligence rather than basking in the fact that it takes us 20 years to learn calculus?
Because they don't exist. As
Doesn't
best
stop
we
you
know.
from imagining. You asked me about other intelligent creatures in the universe. You started this by asking me that. And I'm
did.
saying that imagine on this planet another branch of primates with a similar difference to us that we have today. That's not hard to imagine.
But you wouldn't.
We got the primate family
You
already.
wouldn't let me. When we started this, you wouldn't let me imagine anything before the beginning. We were doing physics. You wouldn't let me imagine anything. Suddenly, we're doing biology. You're imagining.
Well, we got no
imagining.
data there.
Well, what data do you
I
have?
can extrapolate very easily.
Oh.
That's not a tough. Is that a tough extrapolation to make? Am I out of left field here? Isn't this a curious thought? Isn't it a spooky thought?
Is going backwards from year one such a terrible extrapolation? Can't you go backwards from year one? He doesn't want to go backwards from year one. But he's going to do it with apes. Anyway.
Just imagine the ape family, and we're just there, one of the ones in someone else's zoo, as they chuckle at the cute things our Einsteins and Stephen Hawkings do. In fact, imagine those toddlers.
Why are we imagining
I got this. Imagine their toddlers coming home from school, and then the parents say, "Oh, isn't that right? You composed another 7 symphonies today in your 2nd grade class. Let me tack it to the refrigerator for when Dad comes home." And oh, is this? Oh, how quaint! You just solved the unified field theorem, as in 3rd grade. Okay, we'll put that on the refrigerator door too, so that when our friends come over, they could be impressed that you're doing basic math.
Am I to assume that we are enjoying this particular colloquy because you believe
Colloquy, is that?
Colloquy, that is conversation, this little new thing that we're talking about, which is a bit
Why don't you
mysterious
just say conversation?
to me. Okay. That we're having this conversation because you believe that a small change in DNA, not unlike the difference between us and
It's not because I
chimpanzees.
believe it is. It already is that way between us and chimps. It's not like some belief system. I'm just handing you increments to try to keep us honest about how we think about ourselves in this universe.
But I asked you, what are your feelings about the possibility of other examples of intelligent life? And you're answering, well, I can think of something more intelligent than us. I said, okay, but what about as intelligent or even intelligent or not like a rock? Or not like a fish, a dumb fish.
It may be that intelligence is rare in the cosmos. Intelligence as we have defined it. Because if you look at the fossil record, you look at the portfolio of life that has lived and thrived on Earth, there are a lot of features of life that many different species have in common. For example, locomotion is a pretty common talent. In fact, we have creatures on Earth with no arms and no legs, and they still manage to move. We call them snakes, okay? So locomotion, they figured out how to move even though they don't have arms and legs. Trees haven't yet figured out how to move, except in The Wizard of Oz. But what we have is evidence of features in life that apparently are really good for survival. The capacity to receive information at a distance, that would be the smell, hearing, sight. Sight is a very common feature in animals. In fact, there are certain expressions of sight that happen independently of each other. That's how valuable this was as a tool for survival. The fly eye has nothing whatever in common with the vertebrate eye, itself having nothing whatever in common with the octopus eye. Yet they are all eyes and they all see. Let's look at intelligence. Intelligence, as we have defined it, has shown up nowhere in the fossil record, which tells me that intelligence can't be all that important for survival. Otherwise, it would have been there in the fossil records. It would have been there manifested multiple times throughout life. But it's not. In fact, you can continue this to its extreme and say it may be that intelligence is just the right thing to have to render yourself extinct. Thereby cutting off your gene pool from the rest of what would ever happen in your lineage.
Wait, this is getting sort of sad all of a sudden. Because it sounds like now you're conceding maybe mind or intelligent life is a rare thing and maybe a self-destructive thing and maybe an unnecessary to procreate and thrive thing, and therefore we may not find many of them.
There's a fascinating idea, which is a little bit of a stretch, but I want to share it with you. And forgive me, I forgot who the original proponent of this idea is. It is not mine. The question is, if there's intelligent life everywhere, vastly more intelligent than we, presumably they might have figured out how to travel through the galaxy and get wormholes, whatever. And why aren't they here? Why haven't they visited us? Why haven't they taken over the galaxy?
Well, row 2, of course. But
Row 2, yeah, it's sitting in row 2. So one argument is that the very behavior trait that would have you want to acquire territory is intrinsically self-destructive. Because to want to say, I want to put my people in more places in the galaxy, well, if that's the attitude your species has, then other people that you put there are going to have that very same attitude. And they're going to want to do what you're doing. Everybody's going to want to do what you're doing. And you know what happens? You're going to end up fighting about it.
well, it's a big place.
No, you're going to
Lot
end up
of
fighting
room.
about it. That's what they said about the Earth. It's a big place. Said that 600 years ago. It's a big place. No, it's a small place. If you've got ways to get there quickly and efficiently, it's a small place. And so it may be that the very character trait that would have you take over the galaxy and visit every planet is the one that would prevent you from getting there because you would have killed each other in the act of trying to make that happen. So that trait is self-limiting.
Huh.
That's a fascinating bit of sociology, I think.
Hey, you were the pro-life people. Now you're there. I guess we're all going to be dead people.
Now, why did only this half of the room applaud to
I
that?
don't know.
I don't know. No.
All right, let me ask one last question. There are a group of people. There are two groups, really. There's one group of people that strike me as kind of poetic, and I find them interesting. These are people, they're physicists, many of them, who say that there is something so special about the universe and us being here that they can't quite escape the idea that somehow the universe, a fundament of the universe would be to have the rules of physics, to have gravity and the properties of quarks and atoms and stuff, and to have something called ultimately mind. That mind is somehow written into the code of the universe, maybe because
Mind, as in
as an intelligence, so that when you have a universe, what you are inevitably going to get is something that can appreciate the thing that it is in. And this is called the anthropic principle, broadly speaking. And I wonder, I assume you're very hostile to this notion, but I wonder if you have any.
what was the universe saying before we were around, which was not long ago?
It was
back
saying-
when dinosaurs were ruling the world.
It was
what,
saying-
what would this philosophy have said?
We're waiting for the people to have a mind.
Well, that seems to me to be an extraordinarily inefficient universe if it takes 13.7 billion years to produce us. That's just really inefficient if its point is to produce us. Why
Well,
did it happen like immediately? After the 200 million years of the big, pop, there we are, appreciating the formation of the,
Well,
of,
it gets
of the
to-
solar system.
it get-
No, let's have 3.5 billion years of single-celled life first, okay? And well, they're going to
Wait,
crank out the
before you
oxygen.
spit
let's
on
have
this idea so
fishes
much.
first.
Let-
Let's have plant life first. Let's have ferns. No, let's have T-Rex dining on their mammal ancestors first. It just doesn't sound like an efficient way to make that happen.
Did
It
someone
sounds
say
like
it
the
had to
human
be
ego
efficient?
getting in the way again.
Well, all right. Let me ask it in a different way, and then I'll let it go. Are you not a little lonely to imagine a story, the story you've told here tonight, to be, while beautiful, while majestical, while mysterious, somehow purposeless? That is, it seems to have just happened in some kind of accidental or random way. If you were to ask the deep question, why did it happen this way and no other way, or why are we here, you would end up having to say, until, of course, as you put out, someone brillianter than you comes along, but you'd end up having to say, I don't know, and maybe we'll never know, because it is the nature of this, of the scientific method to not look, to be actually very suspicious of ego, purposes, cause and effects, which reflect nicely upon the thinker. And therefore, you're left, sadly, I think, in the posture of not being able to answer the lonely person's question called, why did this all happen? You can't answer that. I don't think.
I think that's you've constructed it in a way that makes it sound like a lonely question.
Yeah.
But let's go back in time, okay? Why did the lightning bolt strike the temple? Okay? Well, because the temple's the highest region and thing, and it conducts electricity, we later learned. Okay? There are a lot of why questions that used to be mysterious. And someone back then would have asked it in the same way you just asked the why questions then. Why do some people take ill and die? Oh, we will never know. No, there's germ. They just like drank a vial of E. coli. You know, I mean, there are causes and effects of things that have been revealed over time that were previously left to the mysteries of the universe. And so I am not quick to chalk up modern day mysteries to just simply, we may never know. Because the success of the methods and tools of science has been such that I retain a level of confidence that going forward, whether or not in my lifetime, perhaps others, we'll probably figure it out. And if the day comes where we actually can show that something is unfigure-outable, that'll be an interesting time. But I'm not going to believe that I'm living in that time now, because people have made that mistake for millennia before us.
But what you will figure out, I think, is how. You'll say, somebody...
Oh, see, now you're converting the why to a how.
Yeah.
No, the person says, why is it that we die? We know how we die, because after we figure it out, it's no longer a why, it's a how, okay? Because now we know how it is, and you're denying the word why from that answer now. And that's not fair. Just because we figured it out, you can still call it a why. Why did we die? Because the cell gave up the ghost, they did this, or you got infected with a bacterium. We have answers that used to sound like, to questions that used to sound like the questions you're asking now. So now, why don't you, in front of this witness audience here, come up with some why questions? And we'll wait 1,000 years and see if they're solved. And we'll come back and we'll find out who's right.
My very last question has to do with a gang of scientists who sort of new on the block, who seem to think that scientists who ask too many why questions or who turn to God for the answers to those questions are really bad guys and should be watched closely, if not chased around the block. So you get, say, Professor Richard Dawkins. Well, let's see. You get. Let me see here. You get Nobel laureate Steven Weinberg. Anything that we scientists can do to weaken the hold of religion should be done, and maybe in the end, our greatest contribution to civilization. Richard Dawkins in The God Delusion says, anyone who believes in an Old Testament God is believing in, and this is, I'm quoting, is believing in a petty, unjust, unforgiving, control freak, a vindictive, bloodthirsty, ethnic cleanser, misogynist, homophobic, racist, infanticidal, genocidal, filicidal, pestilential, megalomaniacal, sadomasochist, capriciously malevolent bully. So I'm wondering, now you actually ran into this crowd out in California. And,
I spent a couple of days with them, yes.
Yeah. And now I know that you share many of the feelings they have, but their mood is somewhat new. They worry that in the Middle East and all over the world, these people who are these godful people, who in their view are very, very sure of themselves and often in their view fanatical and sometimes come armed with either suicide's ability to blow themselves up or worse, some of them now in Iran may have terrible weapons, that these people, because they are religious and because they have technical and scientific knowledge, are dangerous people. And they act like they're dangerous people, and they get scared, and they say these terrible things about them. I'm wondering, why do you think this is happening, and do you agree with it?
In 30 words or less?
Yeah.
Yeah, I think I understood the question, I think. I think the issue here is not specifically with regard to religion. One could abstract the problem away from religion and address the problems that come about when a person or any group of people are certain that they have access to the unassailable truth that others do not. And this can happen with or without religion.
Yes.
It can happen with scientists, as it did in the Nazi regime, for example, where they had a belief system, a eugenical belief system, that in their judgment was unassailable, that the Aryan race was the leaders of all humanity. And so when you are a part of a system that has a dogmatic belief, it is not subject to comment, to criticism, to revision. And anytime you have a belief system that's not subject to revision, you have a combustible mixture when that system has access to power, as was true in Nazi Germany. I mean, it's as what is true in religious states that have access to military power. If they don't otherwise have access to a military power, then it's kind of just an innocent belief system. It's not hurting anyone. And so, unlike Dawkins, I'm not going to run around tell people what to believe and what not to believe. I'm not interested in that. That's not my mission. And in fact, as barbed as those words were, I didn't even know there were that many words in the dictionary that could do that, all right, in that sequence. But if you hear him speak those words, it's even more barbed. And I've actually had a rejoinder to him at the very meeting where a lot of this came out. If you do YouTube, Tyson Dawkins, those three words, Google YouTube Tyson Dawkins, you'll go straight to a clip of me saying to Dawkins at a workshop that he, being professor of the public understanding of science, when he carries on that way, he actually turns off half the people who he's trying to communicate with. So that makes him a lesser communicator if, in fact, he's trying to communicate an idea. It's actually rather divisive. And so now, if you want to be divisive, fine, but then just don't call yourself a communicator if the only people who listen to it are those who already believe what you're saying. Communicators convince those who don't otherwise know what you're talking about into what you say. Effective communicators. So my point is, and I lost track of where I was.
Well, what I'm wondering is, do you condemn Richard Dawkins for using these words? Or you just sort of say, well,
right. So I'm saying
you're not making your point very
so,
well.
So all I'm saying is it's the so where I come to the issue is, like I said, I don't care what you believe. It doesn't matter to me, provided it doesn't harm another person. However, if what you believe is demonstrably false and you want to pass it off as true in a science classroom, I have an issue with that. If you want to say it in the religion class, fine. In the belief system class, fine. In the history of human thought class, fine. And I don't know how many of you, I managed to get like a little letter to the editor in the New York Times a month ago. Do you remember that case in New Jersey where there was the middle school student who tape recorded the history teacher saying that the students will burn in hell if they don't believe in Jesus Christ? Do you remember that? And it became a whole hullabaloo in the district, and they would say separation of church and state, this is a violation of the First Amendment, or Second, whichever amendment, okay? First Amendment, separation of church and state. And everybody got up, and the American Civil Liberties Union, everybody's jumping in arms about separating church and state. And I'm saying, among the statements made by this teacher were that the Big Bang and evolution were not scientific theories, and that Noah's Ark carried dinosaurs. Now, so at some point, I said, I can't keep listening to this. And I wrote a really short letter. Short letters are the best, I think. And all I said was, after two other letters rambling on about keeping religion out of the school because of the amendment in the Constitution, I said, this is not an issue of the separation of church and state. No, you got that wrong. This is an issue of the separation of ignorant, scientifically illiterate people from the ranks of school teachers. And so here's a person. Now, I cited in defense of that line his comment about the Big Bang and evolution and dinosaurs with Noah's Ark. I did not cite in that his assertion that Jesus Christ is a savior, because not much I can say about that. But to pretend that the rest of this information, that he's accurate in this information, that's a travesty. That anyone who calls himself a teacher would believe that as factual information about the history of the world. That's when I jump up and I have something to say. Right. Whereas my distinguished colleagues here are ready to run out and, and they're ready to run out and sort of change the world. I'm not, religion's here long before science ever was. Every culture there's ever been has had a religion. And so I'm not here to try to change that. There's some rich things that have come out of art and music, and there's a lot there. So it's not like science never been used for nefarious purposes. And it's not as though all leaders who caused great war and destruction were religious. Others were secular, like Pol Pot, and Hitler was not associated particularly with anyone. So I'm not here to have that debate. I have a limited budget of time, energy, and capacity to share with people an understanding of how the world works. And I just keep it in that domain.
Well, we have a limited budget. It's 9:45, which this is a little longer than we. Yeah.
That's long. We can't end without me describing what happens, how you die and you fall into a black hole. Can I just say that, and then we could call it a night?
Well, we have
I know we're going a little long
why
here.
don't we have somebody? Well, here we could do this if you want. We could lift up the lights. People who have to go back to babysitters and whatever could walk away. People who want to stick around and ask questions, and then we can lead with what would it be like to be falling into a black hole and get killed by one? Would that be?
All right.
So
this is like a temporary ending. This is an intermediate ending. So thank you for coming.
Yeah, those people who have to
thank you.
head off. So we will understand for those of you who have to go. For others of you, so people who are in the middle who want to get out, they could just head out, and people on the sides could. Meanwhile, just during this warm-up period, could you describe if, for example, the woman leaving there in the back were to instead go to the event horizon of a black hole and fall in, what would happen to her?
That would be bad. You can calculate how this will work. It turns out you might not have known that as you sit there, as you stand, your feet are closer to the center of the earth than the top of your head is. Of course, that's obvious. But what we don't carry with us as a general bit of information is the fact that Earth's gravity is pulling more strongly on your feet for being closer to the center of the earth than it is pulling on your head. It's not enough to notice, so we don't live with that awareness. But in the vicinity of a black hole, if you do a feet-first dive, it turns out that your feet can be materially closer to the center of the black hole compared with where your head is. In other words, on Earth, if you're 5.5 feet tall, Earth is 8,000 miles across. So that difference it's nothing. But suppose the center of the Earth were like right here, and the distance to the center was, your height was large compared with the distance to the center of the Earth. Then you start feeling this difference in gravity. By the way, that's called the tidal force. That's what stretches the waters on Earth, okay? That's why you have tidal bulges on the Earth. So that can happen to you. So you're falling down, let's just say it's a feet-first dive. And as you descend, the difference in gravity between your feet and your head begins to grow. And it first kind of feels good. What's the first thing you do when you wake up? Stretch. You want that to happen. Then you realize that the act of stretching is unrelenting, okay? And what begins to take place would be the envy of the Spanish Inquisition, okay? Because you just continue to stretch, and you can calculate the stretch point where the difference in gravity exceeds the molecular bonds that hold your flesh together. And so there will be a point where your body snaps into two pieces. You will likely break at the base of your spine. in that first of your bifurcations. Then those two pieces, as they descend, will feel the same thing your whole body felt a moment earlier. And then they snap into two pieces. So go from 1 to 2 to 4 to 8 to 16. And then you break up into a myriad of pieces as you descend to the center. And that's not even the worst of it. Because what's also happening is the fabric of space and time, as described by general relativity. General relativity, gravity is not so much a force, but the shape of space-time. The shape of space-time funnels you from what was once a wide area down to a narrow area. So that in fact, while you're stretching, you're being extruded through the fabric of space, like toothpaste through a tube. And in fact, the product, there's a word for that. We have a word for how you die falling into a black hole. It's called spaghettification. And so the title chapter of Death by Black Hole, the chapter is called, in there is a chapter called Death by Black Hole. And it's much broader than that because black holes wreak havoc on their environments. They're scary things because they can eat you. Mm-hmm. And humans tend to be scared of things that can eat them. That's why kids love T-Rex more than they love the Brachiosaurus, which just chews on leaves, okay? They like T-Rex because it can eat a kid, the way a black hole can eat an adult. So there's a whole section there on ways the universe turns bad. And so so it's an introduction to that not being the only way you can die in the cosmos.
Well, now you know.
I have to announce before, because now that the light's on, I can see like who's here and who isn't. I'd like to publicly recognize my longtime editor at Natural History Magazine. I see her there, Avis Lang. Would you please stand up? Avis Lang, stand up, please. Stand up. She's right there. Okay. Avis Lang. It's editors that make writers look better than they ever deserve to look in the final product of what makes it to the page. And I want to publicly thank you for your efforts in improving all that I say, making sure that I mean what I say and say what I mean.
Well, I don't know how much time they'll let us have, but let's try a few questions. About 3 or 4? Okay. Over there, yeah.
First, I'd like to thank you, Robert Bowers, for the wonderful evening. Dr. Tyson, very quickly, are you an optimist or a pessimist on trends in scientific literacy and appreciation for epistemology in world society, and especially this country?
You asking me? Dr. Tyson, okay.
One of the words you used was epistemology. I try to avoid words like that. You heard me complain about this other word here. You think just the nature, just what is the future of the interest that the public may have in just learning about our place in the universe and the literacy that comes along with that so that we can actually trust that there will be a tomorrow for those who follow us. Is that a fair rewording of the question, or have I missed a philosophical point?
You've missed the nuance, but we won't get into it now. It's here in the museum.
Okay. But I don't want to miss your nuances. I mean, fix the nuance that it might...
You can go give it another try.
Yeah, give me the nuance. And use 1 and 2 syllable words.
Being curious and exploring the world, as you say, and using reason and all that is very important. But I think the most important thing, the most important lesson learned from it is an appreciation of how we know what we know, which is to say, in a $50 word, epistemology. The scientific method and how it applies to many other questions, political and otherwise.
Yes. It turns out that in life and in school, you don't always have the luxury of time to learn how everything that we know came to be known. They just don't have the time for that. So, so you want to pick and choose those that were kind of most significant. How do we learn that the world was round? How do we learn? So you pick and choose. And in this book, I spend like a disgusting amount of time sharing with the reader how we came to know what we know so that you can look at what we now say about the universe either with joy and with a healthy dose of skepticism. So that is an important dimension of moving forward. But what I think is more important than the epistemology of things is simply, if I had to choose that you knew one thing about science, I would care more that you just simply had a healthy dose of science literacy, more than I would care that you knew how we came to know everything that we know. And there's some overlap in those two, of course. But science literacy is just kind of knowing not so much how your microwave oven works. That's an aspect of science literacy. But the biggest part of science literacy is knowing how to think. Yes. What is the wiring of your brain? When someone says something to you and claims that it's true, do you have the capacity to judge it and assess the likelihood of that statement being true? Do you have the capacity to ask a question? Because I can say extraordinary things, that particles pop in and out of existence at an atomic level, and then you can, I don't expect you to believe it, but I do expect you to ask me questions. Why do you say that? How do you know? Then I start citing experiments, and then I agree with you, it's freaking weird, but that's how nature reveals itself to us as we investigate it. So, now let me get back to your larger societal, cultural point. I don't believe we can expect broad-based science literacy in this culture unless there are funded big dreams laid before us so that the next generation of students can look to it and say, I want to land there. That's something we took for granted in the Apollo era. We were going to the moon. This was a mission statement that the nation took seriously. And you had to beat people back at the door who wanted to become scientists. There wasn't, how do we get people interested in science? That was not the problem in the 1960s. There was a flame under our rear. Sputnik had been launched. We were losing the space race. There were these drivers, much larger than just the inspiration factor in the classroom. There were drivers outside of the classroom, and there's no greater driver than just such vision statements. So, I serve on the board of NASA. It's an advisory board, not a control board. We can just kind of suggest what to do. NASA has some of the greatest power there ever was to stimulate human curiosity, just by laying out a vision. And the budget that NASA occupies in the full accounting of the federal budget is minuscule. Most people complain that NASA's spending too much money, don't actually know how much money NASA is spending. On your tax dollar that you pay the government, NASA spends 0.7 of 1 cent of that dollar. That's the entire space station, space shuttle, all the space missions, all the Hubble pictures, all of that is 0.7 of 1 cent. And like I said earlier, we're a wealthy country. You can, that's cheap. For the universe, you're buying the universe here, thank you. So, if one of my goals is to make sure that there are big, grand vision statements that the nation can lay down so that we can stimulate a whole next generation of curiosity about the frontiers of space exploration. And space exploration today is the search for life, search for the chemistry of life. So you can get the chemist, the biologist, the geologist, the astrophysicist, the physicist. There's a cross-pollination of disciplines that is without precedent, simply because certain scientific questions that have gotten asked requires that cross-pollination to answer. So I am hopeful, but struggles remain, and I'm working on it. Okay, thank you.
Way in the back, so you're wearing a purple, you have dark, long black hair. You just put down your hand because you wondered whether I'd found you. That's you, yeah. Can you stand up? I'm having a little trouble.
Well, I heard it. She said, can you travel through time in a black hole? Was that the question?
Yep.
Okay, that would not be your biggest concern as you're becoming spaghettified. I don't think that's going to be your priority. But let me answer quickly. As you accelerate and as you find yourself in the presence of high sources of gravity, your time actually slows down as viewed by others. Okay, this is part of the relativity of time. And so you basically slow down. And then you come back, you will be younger than your twin sister that you left back here on Earth. And That's just true. We've known that since 1905, that this is the kind of thing that would happen. That, in a way, allows you to travel into the future. But the question is, can you travel into the past? That gets a little risky because suppose you prevent your parents from meeting each other. Then how would you be born and then become the person who goes back to prevent them from meeting each other? See, so you get some internal contradictions there. There are people who are working on exotic solutions to Einstein's equations that allow backwards time travel, but they're exotic beyond measure at this point, and not something that is an ordinary consideration. We used to think, not because it was proven, but because it was fun to believe, that you might go through a black hole and come out the other side in another place in the universe. Hawking, a year and a half ago, demonstrated that that's not the case, that all the information that you contain that falls into a black hole actually stays there, and later on evaporates out in the form of Hawking radiation. What a coincidence. Hawking radiation, and we can account for all the atoms that went in by the evaporation of the black hole that comes out later. So you didn't go anywhere. You just simply got spaghettified. So no, don't look to black holes as as some hope for your next science fiction story.
And you can be last.
Plus, I told you to avoid them. That was my first line here today.
Go ahead.
That's an excellent question.
The question is if there are multiple universes and some of them have a different set of rules, physical rules, than other universes, what is the reason to believe that? Why do you
Okay, let me first back up for a quick moment. When I say different laws of physics, I don't mean some other list. I mean, look at our laws of physics and then make small adjustments to them. Okay, so that's what I mean by a different laws of physics. The multiverse, it turns out, let me back up. In the 1920s, quantum mechanics was invented, discovered, however you want to think scientific advances take place. Quantum mechanics is the study of the small, how particles behave. And we learned that if you get to a small enough scale, you lose the ability to predict with precision the behavior of the system. And you can only describe it statistically. And there are ranges of things it can do, and all you can describe is the range of properties that it may have. Well, here's this big grand universe we have described by Einstein's general theory of relativity. But at the Big Bang, the entire universe was the size of an atom. And so you have the need to have the physics of the small, quantum mechanics, marry the physics of the large, general relativity, because they're occupying the same space, if you will. Now, when you take quantum mechanics and apply it to aspects of the fabric of space on that scale, what you have is a gurgling of the fabric of space-time. In fact, it's been called a quantum foam. This gurgling is because quantum mechanics prevents you from knowing anything with precision about the system. So you can't say, here's a spot on that grid. That spot is this undulating, pulsing foam. And so now, when you look at this foam, applying the laws of quantum mechanics to it, you realize that this fabric is not limited to one zone or another. In fact, there's a region of the fabric that could hatch out an entire universe with the variations in the laws of physics simply because the conditions that would spawn the laws of physics had variation in them. And so the multiverse is not just some invention out of the ether. It flows out of an application of quantum mechanics to general relativity. We're not completely there yet with a full solution, but it's why the idea is taken seriously. It's not just an invention. It flows out of this application, and it has philosophical precedent, because we thought we were the only planet. No, there's other planets. Thought we were the only star. No, there's plenty of stars. Thought we were the only galaxy. No, there's a billion. Are we the only universe? Maybe there are multiple universes. So there's historical precedent as well as theoretical foundations for it.
Although one could, in conclusion, really wonder why there would have to be Neil and Robert here, Neil and Robert without hair, Neil and Robert without your tie, Neil and Robert without this mic, Neil and Robert without that water, Neil and Robert without your question, Neil and Robert with you, Neil and Robert without you, Neil and Robert with you and him.
If
maybe
there's an
with him and you.
infinitude of universes, that's a trivial extension of this moment.
It seems awfully, awfully, awfully ornate, but since you're all here or not here, we thank you all for coming or not coming, and for listening or not listening as you are. Thank you very much.
Thank you.